Hello, welcome to your virtual Physics 202 lab. My name is Caillou Davison. I'm a TA in the physics department, and I'm going to work with you guys today for your lab number 6, I believe, magnetic fields and forces. I taught 202 lab last semester. I'm teaching 207 this semester, but I certainly I'm not rusty on my 202 lab. So I'll give you a quick introduction. Again, I'm not a TA for the 202 labs. So the person who's going to be grading your labs will be your regular instructor. I'm just going to be walking you through this lab today. And so when you're completing your lab, please consider the expectations your lab instructor has already basically told you about, so that you can fulfill those requirements as they're expecting you. For instance, if your lab instructor is expecting the correct number of significant digits, make sure that you're doing that in your labs. If they're not, then you still should be doing so, but you may, if they haven't told you that they'll take points off, then that's just a place where maybe you won't worry about getting points lost. Anyway, so it's still going to be your regular TA grading your papers. I'm just going to be walking you through this particular lab today. There will probably be various different instructors for various different labs as we go on for the rest of the semester. And again, thank you all for your cooperation in staying home and preventing the spread of COVID-19. It's the action the school has taken to close classes really will lead to lives being saved, possibly lives being saved because of this particular class that you're in not meeting. It can be to that small of a level. Anyway, so without any further ado, make sure you've watched Samantha Wickramarakis, Dr. Samantha's introduction video. It's very important. It tells you all about how you're going to be submitting your reports and how to access the data, et cetera, for the labs we'll be working on. Furthermore, if you have any questions, there will be Zoom video conference meetings available for you to talk to a TA. And those will be listed on the Blackboard page so that you can ask any questions. I know that the big, most important reason we do these labs is so that you get a hands-on feeling of the concepts you learn in lecture in real life, as well as getting a chance to perform the experiment yourself and be able to present your findings. So while we can't do the first hands-on part, we can do the second part, and having your TA available to you to talk on a conference meeting will have you be able to answer questions and, I guess, interact directly with the work you're doing. So you'll be able to get a sense of any difficulties you're seeing will be answered. So without further ado, let's get started on Lab 6, magnetic fields and forces. First thing we're going to talk about are magnetic field lines. So we've talked about electric fields in the previous lab. Today we're going to be talking about magnetic fields, specifically magnetic field lines. You've got a couple questions in your pre-lab about magnetic field lines and magnetic fields. So it's important that you have basically two concepts down for the magnetic field lines. First of all, magnetic field lines always go from the north pole of the magnet and then point along and end at the south pole of the magnet. And you got to make sure that the lines have a direction, and it's always from north to south. So these lines also don't just start and end anywhere. You can't have them just dangling around. They begin on the north pole and end at the south pole. You can't have magnetic field lines that end anywhere else. They can go off the page, that's fine, but they have to reconnect back to your other south pole. It's also important to note that you can't just have a single north pole or a single south pole just hanging out. Magnets always come in pairs, north and south. You can't have a single north pole just hanging out on its own. So when you're doing the your graphs and drawing your magnetic field lines, always just make sure to follow those recommendations, and remember that when you're observing what the compass is doing, that the lines always again go from north to south. And so if you stick another magnet in the mix, then the lines will still go from north to south. They might just go to a different magnet than the one you started on. Now, there's a part where you're going to actually be looking at a picture of a magnetic field we're going to show you a picture of a bar magnet with several compasses around them. You'll draw the magnetic field lines based on what the compasses are telling you. And I'll go into that in a little more detail. There's just one thing I wanted to point out to you, which was, I think it's question number 5, is that correct? Correct. So for question number 5, the first thing we'll need to know again is that when we're doing the magnetic field of 2 bar magnets, we're putting together 2 magnets in a north-north, south-south configuration. So again, what that's looking like would be like this. So 2 magnets next to each other, and I'll show you. We've got these 2 ones right here, and when you're drawing the magnetic fields, we're gonna put these together, and we're either gonna use a rubber band or tape to hold them tight, and we're joining them. So north is next to the other magnets north, and south is next to the other magnets south. It takes some force to hold these together, but just to show you on a diagram what that would look like: north, north, south, south. So you can see that there's some glare, but that's you see what I'm talking about. Now, for question number 5, it asks you to figure out how the fields and field lines would look like, how the total field would look like if we line them up the other way. So we took north on one magnet and then south on the other one and stuck them together as such. And then I guess the question is asking specifically, if they're allowed to attract and stick together, again, north to south and south to north, what happens to the total strength of the field, and why? And just, I'm not going to give you the answer, but I want to prime you on the answer, just to give you something to think about. This is what we set up in the experiment that we're going to look at and draw the field lines. And then this one here, in pink next to it, is what the scenario in that question is, where we have north next to south and south next to north. So be sure, if you're having a little bit of trouble with that question, consider drawing the field lines in this second configuration. And remember, of course, that they start at north and end at south. And consider then if the force, how the force will be affected. And one more point about the magnetic field lines is that they don't cross each other ever. They just always, they go in their own path. It's up to you how many you want to draw, but in that part 1 where we're drawing the field lines, I recommend drawing certainly at least 6, possibly 8, just to get a good feel of them. Again, they don't cross, so you don't want to draw too many or else you're going to run out of space. But you want to have enough that you have a good picture of how the field is changes with space. So 6, 8, 10, whatever you feel like you can draw neatly. You'll take a picture of that and you'll upload it to Blackboard so that the grader can grade your work. Now, part 2 of this lab today is going to be more magnetic forces and how magnets affect moving charges. Now, for electric fields, we saw earlier that an electric field will have a force on a stationary charge as well as a moving charge. Now, for a magnetic field, magnetic fields only have forces on moving charges. So the equation for the force due to a magnetic field is going to be F of your FB. B is usually the variable how we represent a magnetic field. So the force of the magnetic field, B, that's newtons, is going to be equal to QV cross B. And I'll break that down. Q is the charge that it's acting on in coulombs. V is the velocity of that charge. And note it's a vector here because it depends on what direction it's in. B is the magnetic field, and that's also a vector because it has a direction that it's working on. And now finally, we've got this cross here. The cross is called the cross product. It's how you multiply two vectors together. It's one way of doing it. Now, a cross product multiplies two vectors together and gets a third vector out of it. And so it's a little complicated, but generally speaking, the one way of seeing that is that if the two vectors, the third vector that you get, this is a force. I should put a vector sign there because that's also a vector. The force is always going to be perpendicular to both the velocity and the field. And it's going to be strongest when the velocity and the field are at right angles to each other. That's how the cross product works. In what we'll be doing in this lab and generally in this class is mostly not going to worry about cases where the velocity and the field are not at right angles. So generally it's just going to be equal to just the multiplication of the two. And that happens again when they're at right angles. If they're not, an easy way of doing it is simply multiplying them all together. So that'd be Q times V times B. And then multiplying it by the sine of the angle between your V and your B. So again, if it's 90 degrees or 270 degrees, that's going to be at a maximum or minimum. So sine of 90 again is 1. And so when they're at right angles, 90 degrees, you have a maximum of your force. And that's just the same as just multiplying them together. You can just multiply by 1. Now, what that also does mean, though, is that if the velocity and the field are in the same direction, then there's going to be zero force. Because when sine theta equals 0, when theta equals 0, sine theta is also equal to 0. So a charge moving along a magnetic field is not going to experience any force. It's only when you're moving across a magnetic field that the charge experiences a force. Now, in the case of this lab today, we're not going to be working with isolated charges. We'll be working with currents. So currents are just charges moving with time in a wire generally. And so we have another expression basically derived from this top one. And I'll put a vector sign on this one as well, that your force is going to be equal to the current times the length as a vector crossed with the magnetic field as a vector. And same deal works with the cross product. It really just depends on the angle between the two. And it's you can just simplify it as the multiplication of all these in the scalar form times the sine theta of the angle between the two. In today's lab, we're just going to be working with a sine of 90 degrees. So that's just going to be equal to 1. But it's still a good equation to know. And again, just to break down each of these components, force in newtons is equal to current in amps times length in meters crossed with your magnetic field in Teslas. Now that gives you your total force there. One last thing to mention is to figure out what the direction of the force is when you've got everything at right angles. You use what's called the right-hand rule. Now, the right-hand rule is a source of a bit of frustration. However, it's also a very quick way to work out what direction this is going to be in. So as long as you're careful and set things up carefully and slowly, you'll always get a good answer. You just have to set it up correctly. So 1 second, I'm going to get a chair. So for the right-hand rule, now we've confirmed that the image in your video is correctly right-handed. So I'll use my right hand here to show you how it works. I'm sure your professor has already gone over this in lecture, but a second reinforcement always helps. So with your right hand, you'll start by with QV. So QV, that's the velocity, and you use your index finger. So this represents the direction of the charge. The charge is moving this way. Now, next you need to put in that B value here. So for B, you represent that with your middle finger. And it sticks out at right angles as such. So you've got your velocity on your index finger and your magnetic field on your middle finger. Now, when you stick your thumb out, and I'll show you at all angles here, the thumb is pointing in the direction of the force. So a charge going straight here with the magnetic field going in this direction, so towards you, the viewer, is going to experience a force moving upwards. Now, this is the case for a positive charge. Now, if it's a negative charge, that Q becomes a negative, and your B now is pointing in the negative direction, so straight down. That's kind of hard to do if you're not perfectly flexible, like almost everybody. So one way of doing it is just realizing that the right-hand rule applies for positive charges, and you can set it up exactly the same way with your left hand for negative charges. So in the case of a negative charge, again, moving this direction, you have the B field pointing towards you, the viewer, and the force pointing straight down with my thumb. So positive charges on your right hand, negative charges on your left hand, or negative charges, you flip your thumb downwards. You could even say, all right, a positive, negative charge moving in this direction is the same as all right, one more time. A negative charge moving in this direction is effectively a positive charge moving in the other direction. So you can still use your right hand rule. So you just have to flip the direction of your finger. There are many ways of dealing with negative charges. My personal favorite, again, is just using the same setup just with your opposite hand, because it's negative charge, you use your left hand, positive charge, you use your right hand. But you can also represent the QV as, since it's a negative Q, put V in the other direction. Or you can just remember it's negative, so you flip the direction of F. These all lead to the same results, and you can cross-reference the two different ways if you're finding that you're a little uncertain when you're doing that. So without any further ado, let's go ahead and start